All right, we're going to kind of pick up where we left off yesterday, talking about quadratic functions, transforming them into quadratic form. Okay. Yesterday we worked through and said, okay, if I start with something like f of x is equal to ax squared plus bx plus c, we should be able to complete the squared, and by completing the squared, it generates this function here, a times x minus h squared plus k. Okay? Where h and k are actually components that are developed through the use of a, b, and c. But completing the square gave those. So, for instance, we talked through a little bit that h value is created using the opposite of b divided by 2a. Okay. Yesterday we had the example. Let's see if I can find it. We had this example here where we went through and we started. Obviously, it's in that format, and we worked through completing the square to get it in this format. And it turned out that f of x was equal to 2 times x minus 3 squared minus 5. Okay? Well, that's all fine and it works, but the only thing is that it takes time. It's a long process to do completing the square. But completing the square is kind of like an algorithm that you do every single time the same exact way, regardless of the function you start with. So we recognize that if we just do complete the square with this term here is always composed of the opposite of b over 2a. So if I go ahead and look at that function over there, negative 12x squared. Okay, or sorry, negative 12x was the b term. So b is negative 12 over 2a. Well, 2a would be 4, right? Okay. Sorry, opposite b, so it would be positive 12. Positive 12 divided by 4 gives me 3. There's the 3 that goes right there. That kind of makes sense? Okay. And that becomes pretty useful. I'll show you how to find this point here a little bit better than what the PowerPoint says. PowerPoint says we can find that point by doing this. K is always created by c minus b squared all over 4a. Or I guess the b squared is the only thing divided by 4a. That's kind of a pain in the butt. That's not really nice and easy to remember, right? Opposite b over 2a is easy to remember. That thing's garbage. Okay, so I'm not going to make you remember k or try to remember k. But if you can remember x, that will be enough for us to work through a little bit of algebra to find that k eventually. Okay, but that's kind of where we're going today. I want to use this technique to help us transition a function in this format to a function in this format a little bit easier. And as additional to that, we're going to start seeing what is a necessary application for quadratic functions and knowing the vertex of those quadratic functions. What does that tell me for that particular application? What I mean by that is like real-life situations, modeling, recognizing real-life phenomenons, and how we can use equations to represent them. So we'll do that here in a little bit. I want to go through a couple kind of simple, just problems where it just says, here's a function, find the maximum minimum. Okay. So if I go, let's do the first one, f of x is equal to, is it x squared plus 4x? Okay. Just finding the maximum minimum, finding the vertex. Okay. X is going to be opposite b over 2a. Okay, and that's your x coordinate of your vertex, and then the formula is calling that h, right? So opposite b over 2a, so we'll go negative 4 all over 2 times 1, so I get negative 2. So x for my vertex is at negative 2. Now, how do I find the y coordinate that goes with that negative 2? Okay. Finding that y coordinate, or f of x, okay, I should write this as f of negative 2. All I've got to do is plug the negative 2 back in this original function, right? Plug that negative 2 back in that original function. Negative 2 squared is 4. Plus 4 times negative 2 would be what? 4 plus negative 8. So it gives me negative 4, correct? So negative 2, negative 4. So that my vertex then is located at the ordered pair, negative 2, comma, negative 4. Alright? Now, what is also nice about that is that I look at this number up here. I look at my A coefficient, and it was a positive 1, right? So if it's positive, what's the concavity? Is it concave up or is it concave down? Concave up. So it looks like that, right? So what kind of point would that be there? A minimum. So my vertex is a minimum. We can do some other stuff here if we need to. We could say, looking at this, I think this is the most convenient format to look for a y-intercept. What would be the y-intercept there? Yeah, the y-intercept is 0. Okay, if the y-intercept is 0, the height is 0, and the x value for a y-intercept is always 0 itself, right? So our y-intercept is actually the origin. This is kind of the one case where your y-intercept is also a x-intercept. Okay, but we've got enough information here to get a pretty comprehensive graph. Okay, vertex at negative 2, negative 4. Okay, so it's my vertex. A y-intercept is 0, 0. Okay, now that's only 2 points, right? Only 2 points for something that's parabolic. We know we should have some more points, and we haven't found them yet. We could go through and maybe factor this and find other x-intercepts. But let's do this. Let's be kind of intelligent about this, because we should know that for every parabola through the vertex exists a line of symmetry, right? And right now, I have a really good place. I have that point right there, and it's on the x-axis. Really easy to find that distance right there, right? That distance right now is 2, correct? So if I'm going to use symmetry, what should the distance over here be to find another point? Better be 2 as well. So there's my other x-intercept at negative 4. Okay? So that is enough, and we could use more, but that is enough to develop that function, that curve. Okay? Another point, if you said, I want to try x to be 1, and you'd have to find the y value that goes with that, plug in 1 there, I get 5 back. So 1, 2, 3, 4, 5. I get that point right there. Well, if that's 1, what's that distance right there? Yeah, that's 3, right? So what is this distance over here? Also 3. Well, started at negative 2, right? Negative 2 minus 3 going that way would get me at negative 5, right? This y value was 5, so negative 5 comma 5 should be an ordered pair as well. And I think that's maybe a little bit easier, especially the more you do that, the more you get used to doing that. That's a little bit easier than plugging negative 5 in here, square it, get 25, add to it, negative 20. Okay? Gives me back 5, right? So you can use that symmetry idea to help you find additional points. I only use it if this 0 here was like a radical 2. I'm not going to use that symmetry idea. Okay? I usually use it if these are whole numbers or integers. You can do it with radicals and stuff like that, but it's not really easy to graph 1.4144 or whatever. So that's kind of a use, I guess, for finding the vertex. It allows you to find the comprehensive graph here a little bit quicker. Finding these zeros, I could have also taken the function, found the x-intercepts this way. Okay, what's that going to factor as? What comes out of both terms? X. So you get x and x plus 4, right? So that can be x equals 0 and x equals negative 4. And that's exactly what we found using that symmetry idea with our x-intercepts. Let's do this. Let's keep this. I'm going to keep this vertex here. Because we talked about how we should be able to take this function and rewrite it into vertex form, right? Or what your textbook calls standard form, by completing the square. Well, we've already done a lot of completing a square. This was the opposite of b over 2a. This was, what was it, c minus, I don't even know what it is, c minus b squared over 4a or something like that, okay? So that's all the information inside completing a square. But we found, I think, maybe using a little bit easier technique than c minus b squared over 4a for that negative 4. But now that I know the vertex, shouldn't I be able to take that function and rewrite it in this format? Sum a times x minus sum h squared plus sum k. And those h's and k's are those two things. So I don't know a yet. X minus h, so x minus negative 2 becomes plus 2, right? Square that. And then plus k should be minus 4, correct? Okay. Now I didn't know my a, okay, but I want it to be a positive 1, right? Well, if I FOIL this out, does my a become, does that coefficient right there, x plus 2 squared, gives me x squared plus 4x plus 4, right? That a quantity is already a 1, right? So I know that a right there should be a 1. Okay? And then that there is this thing just written in vertex form. Okay? Which I think that it's extremely similar, if not analogous, to completing the square. It does the exact same thing. And we're using the same quantities that completing the square used. Just maybe not writing every single step of completing the square out. Does that make sense? To transition from that format to that format. Okay. The only thing that I worry about sometimes with people is when they have it in this format, they want to say that is the y-intercept. Okay, that's not the y-intercept. That's the y-intercept is only the c term in quadratic function. Because we know the y-intercept for this graph is 0, 0, right? Not negative 4, not 0, negative 4. So make sure you understand that. Let's do that next one. Let's do B. What's the concavity of that one? Is it concave up or concave down? Concave down. So it's going to look. Okay, it's going to be concave down. What's the y-intercept going to be? Negative 5. So make that my y-intercept. I don't know if it's going to be. Not until I find the vertex. Maybe it'll be over there, or maybe it'll be, over there. Does it kind of make sense? I don't know that until I find the vertex. So let's go ahead and do that. Find the vertex then, which you told me it's concave down, so the vertex is going to be what type of point? Maximum. Okay. Opposite b, so x is the opposite b over 2a. So negative 4 over negative 4 gives me 1 back, right? Okay, so the x coordinate is 1. Now we'll find g of 1. Okay, it's going to tell me the y coordinate of my vertex. Just plug 1 in there. 1 squared is 1 times negative 2 is negative 2. Plus 4 gives me 2. Minus 5 gives me negative 3. So g of 1 ends up being negative 3. So now my vertex is located at the order pair 1, comma, negative 3. So rewriting g of x, a times x minus h, remember that's h, so minus 1 squared, plus k, that thing there is k, so minus 3. Okay, now just think about this. We're always got to remember that a is there. We talked about it yesterday. I want to show you again. The way I've got this g of x solved for now is simply showing me only one, or I guess not one, it's showing me a general solution for the infinite number of functions that have that vertex at 1, -3. All this stuff to go. Okay, so 1, -3, so h is 1, k is -3. Okay, so and we see here, click on F, but that is what we have over there right now on the whiteboard. But at our A over there, I don't know what it is. So A can be any one of those functions, but it could also be providing any one of those, right? We know we want one that's going to have an A value of -2. Okay? So the reason it's got to be -2, if you think about it, what did we say our y-intercept had to be? It had to be -5, right? And that's the one that's going through -5. Now, there's a couple different ways you could figure this out, how you could figure that A out. Okay? I think in the last class somebody mentioned, well, if I just square all this, if I go ahead and FOIL that out, I get x squared minus 2x plus 1, right? Okay? Kind of thinking x squared minus 2x plus 1 minus my 3. Okay? I want that A term had to be a -2, right? So what do I multiply this thing by to get that that 1 right there to become a -2? -2, right? Okay. If I plug a -2 in there, it gives me -2x squared plus 4x. So far we got both those things. It'll be then -2 minus 3. Well, -2 minus 3, does it give me -5? All right, so I can kind of just pull down that idea and recognize I never really multiply the whole thing out. I just look at that term right there. If I were to square it, it gives me x squared, 1x squared. I want it to be -2x squared. So put the -2 in. Okay, and now we've created the correct function in vertex form. Okay, we know that the vertex is at 1, -3. So x being 1. Y being -3, y-intercept of -5. There, again, we can use symmetry, because I only used basically 2 points to come up with that curve. But is there a line of symmetry right there? And that distance right there would be 1, right? Okay, so I knew I had the point 0, -5. That's 1. Doesn't that distance right there have to be 1 as well? So what would that word pair there be?
-2, -5, or 2, -5.
2, -5. And now you've got 3 points. 3 points for a quadratic is much better than 2. Okay. You might think, well, last one we factored and we got x-intercepts, right? Is this one going to have x-intercepts? It's across the x-axis? No. Okay. So if you went through the completing the square process, you're going to get 2 imaginary results telling you don't cross the x-axis. Okay? So we do want some other points, and that's how we find them using that line of symmetry. Hopefully you see the comparisons also. This is it's a vertical stretch. It's a reflection across the x-axis. It's a move to the right. It's a move 3 units down. I would do the reflection. If I was using transformations, I would do the reflection before I did the moving of 3 down. I did that reflection before you do a translation. Is that something we can do? All right. Now let's talk about how we can apply this stuff. We've already seen a couple models using the quadratic formula. And if you go back to, I don't remember what section it was in chapter 1, I think. Or it might have been the first section, chapter 2. We had something that looked like this. h of t is equal to -16 t squared plus some velocity, some initial velocity, plus maybe some initial height. You remember seeing that thing? Okay. If you're in physics, maybe you've talked about that using like horizontal and vertical displacement and stuff like that. But that provides us, if you go back to remember what we're doing here, we are, if I just let this be like a, let's see here, how can I write this? Let's call this, vertical displacement. You don't have to write this down. Horizontal displacement. What's happening here, what we're doing algebraically, okay, is I'm throwing an object straight up and straight down, and it's coming straight back down. Okay, I'm throwing it, shooting it, kicking it, whatever. Okay, some type of propulsion that gets that object to go straight up and then straight back down. Okay, so when I graph the locations of that point or that object straight up and straight back down, it's not a really interesting graph, right? Okay, because I'm graphing against how far it moved left and right. It's horizontal displacement and it's vertical displacement. We're seeing it's displaced vertically. It's moving up vertically, but it's not moving left or right. But once we change the axes, okay, instead of doing horizontal displacement, let's take this and refer to it as time. Now things are a lot better. Because now when I throw that object straight up, I'm measuring the height, okay, h of t, it's vertical displacement, but it's across time, and it's going to look something like that, right? And a lot of those questions that we were interested in when we did these problems were, what was the maximum? What was the greatest height that object reached, and at what time did it reach that height? Okay? Well, if I want to find that height right there, knowing this function, whatever that function might be, I can find that vertex now by taking the opposite of b over 2a and evaluating my function h at the opposite of b over 2a, and that gives me the time, and that would have given me the height at that time. Does that kind of make sense? Okay. And then again, if we needed to, they ask questions about, when does this thing return back to the ground and all that kind of stuff. We can use symmetry maybe to find those points of returning to the ground, or just set this equal to 0 and solve for your x-intercepts. But that's an application of the things that we are currently working on. And it's a lot easier to do it this way than the way that we did it in chapter 1 and chapter 2. Okay? So they might give you a function like this and ask you, when does this object reach its maximum height? We simply use this formula. So let's do one. Let's say that I have this object. Maybe I'm going to throw a ball up in the air. Let's say that I throw it up with an initial velocity of 80 miles per hour. Okay? So it's initial velocity times t. And then let's just say that I'm standing on the ground when I do that. Standing on the ground when I do that. So there's no, this plus whatever number out here is the height in which I throw it from. So I'm going to say plus 0. Okay? If I was standing on top of a building, maybe I say, plus 20 feet or 30 feet or whatever. But we're going to stand on the ground and do this. Okay? So we want to know the height that this ball reaches. Okay? So my graph is going to look something like that. And they're asking to find that point right there. Okay? Well, now here's where you got to be cautious. The variable they're using is t. Alright? We've been saying that x is equal to the opposite b over 2a. That's the x coordinate. In this case, it's a t coordinate, right? Okay? It's always the independent variable. I'm an important person. That's why I'm getting all this text message. Or is that you, Jackson?
No.
Okay.
Anybody want to buy a SIM card? Well, they gotta sell them. $60.
Alright. Sorry. So t is the opposite of t or 2a. We should be able to find that pretty easy now, right? Negative 80 divided by negative 32. Okay. What's that equal?
2.5.
Huh?
2.5.
2.5? Okay, so at a time of 2.5, say we're doing this in seconds, 2.5 seconds, we reach our maximum height. Okay? But now we want to figure out what was that maximum height. Well, now all I got to do is take h of 2.5. So negative 16, 2.5 squared, plus 80 times 2.5. Negative 16, 2.5 squared, plus 80 times 2.5. H of 2.5 is 100. Okay, if I did that right. Alright, that's right. So now my ordered pair, for my vertex, my ordered pair is 2.5, comma 100. 2.5, comma 100. Remembering that there is a time, and that there is a height. Okay, a lot of times when you come up with these ordered pairs, I think a lot of people, I don't want to say a lot of people, but people that miss the problems because they just start asking kind of qualitative questions about these things. A lot of people do the math. They can get 2.5 into 100, but then there's kind of a disconnect in what the 2.5 means to us and what the 100 means to us. Make sure you understand that when you're finding the opposite of V over 2A, that's your independent variable. That's your horizontal axis value, and that right now is representing a time. Okay, so that's our second. So that's when the maximum occurs, and 100 is kind of where the maximum occurs, right? That's the height that we have here. That's something we can do? All right. Now here's something that's maybe you want to know when it comes back down to the ground. When does this thing come back down to the ground? Well, there's an axis of symmetry right there, correct? We know it started at 0, 0, right? How long is that distance right there? 2.5. So how long does that distance have to be? 2.5. So when's this thing hit the ground again? 5 seconds. Okay? And that is a lot easier, I think, once I have that information. Okay? I think that's a lot easier than trying to factor that thing, isn't it? But if you factor that, you take negative 16 out, you get t squared plus 5t, or minus 5t, and then, or not minus 5t, t minus 5 would be that binomial left over. And then that's obviously 5 seconds. Does that kind of make sense? So we've seen some of this stuff, but maybe this is a better approach to solving those things. Okay? We're going to, pretty much every time we talk about a new function, we're going to want to see where does this get used. Okay? They're coming up with new math all the time. Okay? If you sat down, you could come up with new math. You could create an algorithm, a process that is consistent with all the numbers that you want to use, and you say, okay, it does this fancy thing every single time. But that math really isn't useful until you can find how to apply that in the real world and how people can benefit from it, right? All right. So this math, maybe when it was first developed, first recognized, there wasn't maybe a use for it. But now we start, recognizing and applying it to real life situations, and there's a use for it. I think a great example of that is, you guys remember working in algebra? You remember hearing the phrase feasible regions? Use systems of inequalities and stuff like that. The guy that was coming up with that stuff and kind of developing that, it was kind of pre-World War II kind of era, beginning of the war. He was coming up with this stuff, and people were saying, yeah, this is neat and fancy and stuff, but there's no application for it. World War II rolls around, and now we need to allocate resources, get troops places, that kind of stuff, and minimize costs. So now they found a use for it, and that guy became very influential in us winning the war. Does that kind of make sense? So new math being developed all the time. It's whether that math has an application or not. So every time we come across something, I want to show you, here was the application. Here is where this is useful. Here's a situation you guys are maybe concerned with. Dealing with gas mileage. Okay, how many miles per gallon when you get out of a new car? Okay, you see this on commercials all the time. They say, this car gets 30 miles on the highway, and he gets 25 miles a gallon in the city or something like that. Okay, but if you read the small print at the bottom, sometimes that might tell you on the highway we were traveling at 42 miles per hour. Who travels at that speed on 75, right? Yeah, and if you guys know, if I'm driving really, really fast, so if I've got this new car and I'm driving 110 miles per hour, I'm going through gas pretty fast, right? But if I'm also driving like your grandma, 20 miles an hour on 75, I'm going through a lot of gas, right? I'm not reaching the maximum, the peak performance of the engine by going at really slow speeds or going at really, really fast speeds. If anybody ever rent a U-Haul car or have to drive in one of those, you probably haven't rented one yourself, your parents. Okay, if those types of cars, even like rental cars from like Home Depot or Lowe's or something like that, might have these where I know U-Haul has it. If you rent a U-Haul, the speedometer, it's color coded. Okay, so it kind of looks like this. but there's regions here. So this is like red, this will be yellow, this will be green, and this will be yellow, and this will be red. And you want to keep your TAC right there to maximize the gas mileage. Does that make sense? Okay. You know, if you're going too slow, it's telling you red and yellow. You're going too slow, you're wasting gas. Going too fast, you're wasting gas. Okay. Keep it in the green, and you're going to maximize your fuel efficiency. Okay. So this is maybe an equation that helps them to design that speedometer, where to put those markings. But how do they come up with this equation? I always thought it was interesting in high school, or even in college, when they give me a situation, a scenario, and they say it's modeled by this function. Well, how do they know that? Okay. Did they just pick these numbers out of thin air? There's a process here. Okay, and the process you guys are familiar with. Kind of bring down here. Come on, there we go. My whole new setup's kind of got me messed up. I want to use a mouse. That thing doesn't work on touchscreen yet. It's frustrating. All right. You know, we'll come back to this picture here, but you guys know this from science. Take an experiment in like Chem 1 or something like that, and maybe you take an object that is maybe a bowl of hot water. Just keep it easy, okay? And let's say our temperature at some time, and then down here is some time, okay? If I take that bowl of hot water at a small time interval, it's going to be pretty hot, right? Take it out of the microwave, it's hot. Take it off the Bunsen burner, whatever, it's hot. And as time progresses, does that temperature start to decrease? Does that make sense? And maybe I do this experiment 3, 4, 5 times, and I calculate all those data points on the same curve, or on the same graph. So I start collecting more data points. And then we say, okay, for this solution, when I leave it on the Bunsen burner for so long or whatever, and then I take it off and let it cool, can I figure out how it's cooling? Okay? And in science class, maybe you took that point there, and you said, oh, let's take that point there, and let's connect them with a line, right? And we do that so that, you know, some of my data points are above my line, some of my data points are below my line. Try to keep that as even as possible. And then maybe even some data points are on the line. But that line, then you have 2 points, you can come up with an equation for it, right? Now you have when you come up with that equation represents this phenomenon of the water cooling, right? Okay, you guys remember calling that the line of best fit? Ever hear that?
Yes, sir.
Maybe the line of regression. Okay. And maybe in algebra you talked about like correlation factors and stuff like that, where maybe I do an experiment and you know, my data points are all over the place. Okay, so maybe my data points kind of look like that. Okay, that would mean my correlation factor would mean basically my independent variable, my dependent variable don't relate to one another, and I don't have maybe a model that can represent this. But in this situation here, think about we're doing particular speeds and then gas mileage off those speeds. The slower I'm going, the less gas mileage I'm going to get, right? Or miles per gallon. Okay. The faster I'm going, the same thing happens. Okay. But as I start increasing my speed, I start getting better gas mileage. But as I go too far, I'm going to hit somewhere where I maximize my gas mileage, but then start going over that speed, my gas mileage starts going down again. Okay? So a company, Ford, Honda, Toyota, whatever, they're going to do this kind of stuff. They're going to take their cars that they create, and they're going to run them through a bunch of tests. Okay? And they're going to fill them up with gas and go drive them. Fill them up with gas, go drive them. And collect data points. They say, we're going to take, 50 cars and fill them in the gas tank up, and we're going to drive them at 10 miles per hour and see what kind of gas mileage we get. Okay? Then we're going to take them again and we're going to fill them up, fill the gas tanks up, and we're going to drive at 15 miles per hour. Okay? Until we run out of gas and see what our gas mileage is. Okay? And then keep doing that at different intervals in regards to speed and see how that relates to that. Then we plot all those points on the same graph and we get a bunch of things, a lot of data points, but what do they look like collectively? They look like a what? Parabola. So they say, okay, we have a parabolic, we have a quadratic relationship here. So they're saying we'll take that point Maybe I come up here and I take that point, and now maybe I take that point there, and I fit a curve through those 3 points. 3 points will always, any 3 points you ever choose, there will be one parabola that always goes through those 3 points. Okay? Call that the quadratic regression. Okay? Sometimes referred to as a least squares, a least squares curve. But that's how they come up once we have 3 points. When I have 3 ordered pairs, if you remember doing this last year, you use your calculator, it'd be much quicker. But you go through a system of 3 variables to solve for that equation, okay, and get that quadratic. Does that make sense? We're not going to go through it right now. We might later on. But I want you guys to understand that this, whenever they give you a model, it doesn't just come out of thin air. There's probably an experiment behind the scenes. There's data collection behind the scenes that helps create that model for this specific brand of cars. Okay, and they're telling us here that the speed that they were going through, they're restricting the domain. They're saying we only tested things from 15 to 70 miles per hour. Okay, so we're trying to find the maximum speed then that's going to, or I guess the speed that provides a maximum gas mileage, and then that should end up between 15 and 70. Okay, so we got negative. It's pretty easy to do. Negative, if we understand the concept of the opposite B over 2A. It actually takes more time to explain where these models come from than it does doing the algebra thing. But that's the function. We want to find what is that speed. So thinking back graphically, 15 is there and 70 is there. Somewhere in between, we're going to reach our maximum. Okay? And it's not going to be exactly in between. So some people say, well, you said everything's symmetric. Well, 15 and 70, maybe I'm looking at our parabola. Maybe from 15 to 70 kind of does something like that. Does that kind of make sense? So it's not symmetric. So we're looking for that maximum value, okay, that provides me the greatest gas mileage. Okay. So here's where I think it's important. A lot of people just do they don't organize their work, and they're careless with their label, and they just write opposite B over 2A. Well, what does opposite B over 2A represent here? Make sure that you put an S over here. It's always your independent variable that the opposite of B over 2A is equal to. Okay? It'd be really nice when I'm done, I'm going to get 2 values to be able to distinguish what those 2 values are with one another. Okay? So speed, opposite B, so negative 3 over 2A. So what is that, negative 1/14? If I take the reciprocal of that negative 1/14, so it gives me negative 3 times negative 14, which would be 42. Okay? So it's nice to know because I labeled everything. S stands for speed, right? So it's telling me at 42 miles per hour, you're going to maximize your gas mileage. Okay? So if you're not in a hurry to get anywhere, drive at 42 miles per hour. Okay? Because it's going to save you money. But now I want to find what that gas mileage is. Okay? So I plug in that 42 into this function. So negative 1/28. 42 squared plus 3 times 42 minus 31. Okay, and just to save a little bit of time, I think you guys can do that. Input. Hopefully you understand what we're doing here. We're just evaluating functions like we did in chapter 2, right? Okay. So you plug that in. I think you get 32 back, don't you? Yeah. Okay. So it's nice to have that label that's miles per speed, or miles per gallon per that speed. So this vertex right here says going at 42 miles per hour, you're going to get 32 miles per gallon. Okay. And now that we can use that model, that's going to be the maximum. When I can say, okay, well, what if I want to drive, what if the speed limit's 55? Can I plug 55 in here and see what I get back for how many miles per gallon I'm going to get in that car? That makes sense? Okay. So you can see then that, we run maybe all these tests as the manufacturer, and then we get to the marketing part of it, and they get to the commercials, and they say, on a highway, they get 32 miles per gallon. Okay. Well, maybe on the highway, they were using 42 miles per hour. Or maybe on the highway they actually plug in, okay, 65 miles per hour, 70 miles per hour, and see what that function produces in regards to miles per gallon of gas. Does that kind of make sense? We understand that application? Okay. What time is it? 48. You're going to also see, because it tends to be a question that people really struggle with on the homework. It's towards the end of that assignment. I don't know what number it is, but it's all about revenue and income. You guys know the difference between, like, if I say profit and revenue and income? You guys know what the difference of those are?
Yes.
Okay. Revenue is just pure money coming in, right? Pure money coming in. Income, same idea. Okay. The profit is revenue minus cost, right? Okay. But revenue, if I'm in the business of making something and selling it, okay, I'm a business owner. The way I determine my revenue is I take how many things I've sold and I multiply it by the price in which I've sold them all, right? That can make sense? So revenue is equal to price times quantity, right? Okay, that's just a simple formula for revenue. I'll give you an example here of what happens. And this happens a lot. In the business world, I might have, just in this case here, I'm a canoe rental business, okay? It says you currently charge $12 per canoe, and you average 36 rentals a day, okay? If I start, just think about this, if I start charging $80 per canoe, I might get 2 people to come in and I made $160, right? But I can still make that $160 if I left it at $10 per canoe, and then kind of entice more people to come because the price was cheaper, right? So we got to think about where's that compensation, that give and take point, where I can charge them the least amount but gain the most customers. Does that make sense? And that will hopefully maximize my revenue. Or maybe I charge the most amount and gain the least amount of customers, but it still provides me a maximum profit or maximum revenue. So this is saying we've maybe done a study, and it says for every 50-cent increase that I have in rental price, I lose 2 customers. But I gain, per customer that's coming, I still gain 50 cents from them, right? So let's say I make one price increase. One price increase be $12.50, right? Okay. I'm going to now have, instead of 36 rentals, I'm going to have 34 rentals, correct? So even though I made an increase and I lost customers, okay, if I go 12 times 36, that number right there is $432. Okay, 12 times 36. So not changing anything with my business. I make $432. Okay. Well, if I make one price increase, okay, and I lose 2 customers, I go to $425. Okay. So I lost money, right? Okay. What was it? 12 times 36? Yeah. Okay. I lost $7. Okay. So the idea is, okay, if I can recognize this pattern, okay, with a price increase of 50 cents, and I lost 2 customers, so that tells me that that price increase did not compensate for the loss of customers. Does that make sense? Okay, because I didn't increase in money. What I recognize here is kind of a pattern. Okay, this is price. So if I go 12 plus 1 times 50, so 150-cent price increase, I'm going to lose 2 customers. Here, if I go 2 price increases, so $1, I'm going to lose 4 customers, right? 2 times 2. Here I go 3 price increases, I lose 3 customers. Okay? So the way I set this up in a chart here is for us to hopefully recognize a pattern. The 1, the 2, the 3, those are the things that are varying, right? The number of price increases I have are varying. So I'm going to call that my variable. Call that X. Okay? Is that X the same X over here that's increasing? 1 and 2 and 3. The 2 over here in parentheses is the number of customers I'm losing. But for every 2 price increases, I lose a total of 4 customers. For 3 price increases, I lose a total of 6 customers, right? So that's my variable, so I get X times 2. So if I look at this, if I want to determine how to set my prices, okay, revenue is price. So we got price of 12 plus 0.5x, okay, times quantity of 36 minus 2x. Okay? Well, if I multiply that out, is that a quadratic function? Yeah. Okay? So let's go ahead and do that. So we get 432. This is what, 18x, and then negative 24x, so is that negative 6x? And then 0.2 negative 0.25x squared. Does you agree with that? Is that all right? So my revenue function, R of x, is equal to negative 0.25x squared minus 6x plus 432. Okay. Well, that's dumb. Oh, good idiot. 2 times a half. I did a half divided by 2. That's 1, right?
Yeah.
Idiot.
Low.
Thanks, Zach. Catching that error. Alright, so we got opposite B over 2A, right? Okay, that's going to tell me opposite of B over 2A tells me the x value. And the x value is the number of price increases I want to make. Well, opposite of B would be 6. 2A would be negative 2. So it gives me negative 3. Now the sign of that's important. A positive number would be a price increase, right? A negative number tells me a price decrease. So to maximize my profits, I don't need to charge $12, $12.50. I need to subtract $1.50 from 12, right? So $10.50 is going to be the price that I want to charge. Because now that's going to bring in how many more customers? It's going to bring in 6 more customers, right? So $10.50 times 42 then will end up being my maximum revenue that I can make in this scenario. Does that kind of make sense? You'll see a question in your homework similar to this. What you want to do is determine through there, it's all written in words for you, okay? So it's a story problem. But you want to determine what are they charging per object, okay? And then figure out an expression that shows the quantity, and you multiply those together to get your quadratic, and then use opposite B over 2a. We'll talk about that tomorrow.
Haley, is there a meeting today for anything? No?